Good morning, Americas, and good afternoon and evening to many of you from Europe and Asia. My name is Mukund Rajamani. My colleague Andrew McLean and I welcome you to this webinar titled Response Simulation for Space Launch Survival. To introduce ourselves, I, Mukund Rajamani, work as a product manager at Maya Heat Transfer Technologies. Specifically, I overlook the structures portfolio spanning tools and technologies for laminates and composites, fatigue, simulation test, distributed computing, solver language translators, and the product and discussion today, which is random vibration response using SA Toolkit. Andy, would you please introduce yourself?
Thanks. I'm a structural application engineer. I've been at Maya for 7 years, and I'm mainly supporting our structural analysis software portfolio, and I'll be covering the demo in the latter half of today's session.
Thank you very much, Andy. Before we dive right in, what is in today's webinar for you? Today, we will touch upon the importance of random response simulation and demonstrate a tool that can help you analyze random response faster and as accurate. Additionally, we'll show you how to analyze fatigue and tie it into seamless post-processing. Through this webinar, you may add comments or ask your questions. Please use the question box on the question bar on the top to ask your questions. We will try our best to address and answer as many as we can. In case we fall short of time, we will get back to you via email. Also, we will engage you as an audience via a short poll on our poll bar through this webinar. Next slide, please, Andy. I'll give you a brief on what we do at Maya. At Maya, we pride ourselves in helping organizations with their digital transformation journey. In fact, we've delivered more than 2,000 successful digital transformation and AI projects. Maya HTT is recognized by Siemens as a top global partner in providing services to customers in North America and Europe. But we're more than just a consulting and system integrator. We also develop software. We've authored more than 30 modules for Siemens that are used by millions of people worldwide. If your goal is to do complex things better, whether that's designing, simulating, manufacturing, or optimizing operations, Maya HTT has the engineering, software development, and AI expertise to help you. We are here to help you move your projects from your concept to completion and beyond. Next slide, please. And with that, straight off the bat, I would encourage you to look at the first poll. The first question there is, what best describes your role in the context of today's webinar? I would encourage you to select any one. This would help us tailor the course of this webinar well. So please take your time to answer this poll to the best of your understanding.
I see we're getting close to half the results coming in, so maybe give it a few more seconds.
Yep.
And maybe I'll share it here. So yeah, I'm sharing the results. I don't know if you can see it as well, Mukund, but we have a bit of a mix. I'd say kind of 20% existing SATK users, and we've got a few that are kind of curious to see what it can offer.
What it can offer from, okay, that will be very good. So I think we are pretty much prepared at this point of time to move forward on the poll. All right, so Let's talk about payload survival here. So launch survival. To ensure that a payload survives the intense conditions of a rocket launch, several critical tests need to be performed during its qualification and acceptance phases. The list shown here is not comprehensive, but just a demonstration of the complexities of going through the certification before launch. In today's webinar, we'll be touching upon the necessity for vibration testing, especially random vibration. The most pertinent certification standards for random vibration are primarily from NASA, the standard 7001, 7002, the GSFC, the ESA for structures and shock, and the Department of Defense. They're widely used in aerospace and space qualification for components, and they might have dual applications as well for electronics and avionics. And then the SAE, they provide vibration testing methods and reliability practices, sometimes referenced in aerospace and hardware contexts. Next slide, please. Why base vibration testing really matters. Vibration sign testing are essential for ensuring payload survival during rocket launch due to extreme mechanical stresses involved. Vibration analysis and simulation assist testing in the form of predicting in advance how the model will behave, identifying resonant frequencies, stress concentrations, potential failure points a priori, and optimize designs virtually, reducing costly redesigns. And to also ensure that physical tests are targeted and efficient, avoiding over-testing or missing critical modes, improving the confidence in the model for future missions and configurations, reducing the need for repeated physical testing, and risk mitigation and cost savings. The combined importance in mission assurance, regulatory compliance, and cost avoidance are the key takeaways for random base vibration testing. Next slide, please. So some of you who are not familiar with the Structural Analysis Toolkit, we call it SATK for short. SATK offers fast and accurate random base and sine-based vibration analysis, which can save you time and allow you to explore more scenarios and innovate faster. SATK for Nastran delivers efficiency and accuracy where other software solutions struggle, with extensive space systems, electronics, and automotive applications. SATK provides advanced post-processing capabilities for general analysis and state-of-the-art analytical tools for base-driven dynamic simulation. To name a few features, SATK can compute peak stresses, account for Gaussian distribution, composite failure metrics in addition to peak stress strain, margins of safety, modal summaries, stress element forces, grid point forces. In the latest version, we've added random fatigue computations that can be performed seamlessly. And the tool is platform independent as well. Next slide, please. The software features that we are about to demonstrate serves the most following important takeaways. One is the ease of use, and two is that the data is all secure and private. All your data resides in your servers and does not have to be shared outside. With that, I'll pass it on to Andy to demonstrate the product. Andy?
Excellent, thanks. So moving into the demo portion of the presentation, I'll present a typical random analysis in SATK, and typically this involves 3 steps. So you need to start with a Nastran normal nodes analysis, and then those results are passed to SATK. So in the second step, I'll run through the setup, and I will also highlight the new features in version 12. I saw in our poll that probably a majority of the people in the webinar actually are somewhat new to SATK, so I'll make sure to make it a bit introductory in nature as I go through it. And finally, I'll show examples of post-processing our random analysis results. So to begin, I'll begin in a pre-post tool. So here I'm going to use SimCenter 3D, but you could certainly use FEMAP as well. And see if this is playing correctly. Is it a little choppy for you, Mukund, or how's it coming through? And yeah, anyway, I guess what I'm showing on screen here is this is really the Nastran model that I'll be using. We have this existing solution 103 where we're calculating our normal modes, and I'm running through some of the basic setup. So you saw on that screen output requests, we were computing our modes up to 125 Hertz. If you're using SimCenter Nastran, there's a few parameters you can specify to ensure you have the right data in the OP2 file that gets transferred to SATK. And you can see the structure is fixed at a single node at the base. So it is base excitation, and that would be a typical setup with a rigid element at the bottom. I also wanted to show this model is color-coded by materials. So you'll see aluminum is in blue, titanium, purple, steel, green. And we also have composite sandwich panels, which are the yellow elements for the solar panels and the antenna. And I've already went ahead and created Nastran groups of elements and nodes, which I will bring into SATK for the demo, and that'll be used to compute margins and request results on specific areas of the model. And I'm just showing here that the model has been solved already. You're seeing some of the mode shapes that we're animating. And for demos, I'm only going up to 125 Hertz, but you could certainly go up to your required frequency in your case. And I'll just summarize what was shown in this first portion. So you can use either SimCenter Nastran or MSC Nastran to compute your normal modes. We can use different pre-posts. So here I use SimCenter 3D. Many of our customers use FEMAP. And I like to emphasize that we can handle very large models and that you can run this normal modes analysis once. And with SATK, you can reuse it for many different sine or random vibration runs. So that's something that's kind of easy to do in SATK that can be harder in some other tools. And
so Andy, a question came by. The question is, does SATK do shock response? And the answer to that is we'd love to chat with you a little bit more in detail on this request. And if there is more interest with reference to shock response, please type on the chat box, and we'll be very glad to get back to you personally to understand what are your needs. Go ahead, Andy.
Thanks.
Oh yes, I'm sorry. And if you have other questions, please do type on the question box. Thank you.
Yeah, absolutely. Feel free to put those in. And just moving on, before getting into the actual random analysis setup, I also like to highlight that SATK has other processors, and one that I like to use in particular is the modal summary. And that outputs an Excel file, which is where I pulled the chart and the table from on screen. So this can be very useful to understand the modal content of your model, understand, for instance, which modes are important for the response. So it will highlight the ones with the highest effective mass. And typically, you might want to check that you have, say, 95% of your cumulative effective mass in each direction. So this can be really nice also for creating reports or presentations. That would bring me also to our next survey question. So I'll go ahead and launch that. And we'd be interested to know, what software you're currently using for random and sine vibration analysis. We've put a few options. You can actually select multiple in case you're using more than one tool. If you're not using one of the tools listed, we'd be interested if you can put it in the other category as well. So I am seeing some responses starting to come in. And actually, while these responses come in, I do see we've got a couple more questions in the chat. So one is regarding whether we could be used with other pre-posts. Generally, I don't see an issue as long as you can pre-post for Nastran, because we'd be using the Nastran solver. For the post aspect, feel free to comment, Mukund, but I think a lot of our results are going to an OP2 file, which is a relatively standard Nastran format. There are some specific results like margins of safety or fatigue, though that I'm not sure if you could load into this other pre-post, so we may want to get back to you on that, like for instance, hypermesh. And I think the other question that we also get asked a lot that I see that also came in is whether we would support other solvers. So at the moment, it is really limited to Nastran. And so we're not supporting ANSYS or Abacus at the moment. And I will share results of that poll. So thank you for sharing your responses. And I do see, okay, so we have about 20% are on the FEMAP Nastran side, and then we've got about 36% in SimCenter 3D. And we do have, yeah, I guess like before, but 20% of you are current SATK users. So thank you for that. I'll go ahead and continue with the next portion of the demo. So part 2 here is actually where we get into SATK and start setting up this random analysis. And so here, existing users, you'll see a very familiar interface. And if you've already used the tool, it sort of starts in the same way. So you start by loading that OP2 file with your normal modes results. And then one enhancement to our workflow is that we've introduced these modeling objects. So you can go in and define groups, materials, and stress cases. So I typically start by bringing in some groups. You can import this from a file, which is what I'll do here. If you're using FEMAP, you can actually bring it in directly from an active FEMAP session. And these are groups of either nodes or elements, and these are used mainly in our post-processing, so for our stress cases, as you'll see in a moment. And so this has really been streamlined, so it's much easier to manage the groups now. You can edit them from this table editor. It's easier to update these, delete them. You'll see in a moment you can edit from here as well if you need to add some missing nodes or elements. And you'll also note here my groups are separating the model into different materials, which brings me to the next step, which is to bring in some material data. You could define it directly in the interface, but I wanted to show here that you could envision having a material library. So I'm going to import that from our new SATK file. And at the moment, the material data consists of strength properties that are used in margin calculations and fatigue properties that are used in the fatigue calculations that you'll see towards the end of the demo. And finally, the other object we have are the stress cases. So this is a much improved dialog compared to what we had in the past. And with a table editor, you can also copy paste from Excel. So I wanted to show that here. So these stress cases, they're going to link materials to elements and also some additional data like safety factors that are used in margin calculations, as well as like a failure mode. So here I'm calculating ultimate margins. And there's some additional thresholds in there for printing text and Excel files. So with those modeling objects defined, I'll go in and start setting up the random analysis. And we start by defining the base excitation input PSD. And I'm going to import it from a CSV to be efficient. Typically, these PSDs are accelerations in g² per hertz. You can see this one has actually been notched at some specific frequencies. And because it's g² per hertz, we give you the option to put in a scale factor to convert it to the actual model units. Some enhancements in this dialog are that we let you modify the interpolation method, and the frequency range there for calculating results can be inherited from the excitation function. And typically when you run these random analyses, you might have to run 3 different axes. So I'm defining 3 load cases here. So you can see it's quite easy to do that. You could use a different PSD in each direction, but for brevity, I'm using the same one in this demo. Some additional inputs are things like, do we want to use all of the modes? Do we want to account for modal truncation? So I'm activating that. And here I'll choose absolute, but you could also compute relative results. And you need
Hey,
some
Andy.
amount. Yeah. Oh, pause. Yeah.
There was a question that came by. Sorry to interrupt. There was a question that came by with reference to the XY plotting frequencies.
Mhm.
Do those affect the computation or the results?
No, that's a great question. So these plotting frequencies, so you'll see that in the output requests, really just controls the resolution of any function plots that you do, but it has no effect on the calculation of peak or RMS results. So for those results, SATK automatically determines what frequencies to use to ensure accuracy. So that is kind of an important feature.
All right. Okay. Very good. Thank you.
Yeah, thanks for that question. And yeah, I think that brings me then to, we have this analysis parameters, which is where I often will pause to give a bit of background. So you'll see at the top we have a confidence level section. So you have to remember that random analysis is about computing responses for a given probability. And we give you the option to either input a chosen confidence level in terms of a number of standard deviations or percent. So we call those peak results, and typically engineers want to compute 3 sigma peak results. And alternatively, we can also compute RMS results if you wish. So RMS would be equivalent to like a 1 sigma confidence level. And most other commercial codes will only compute RMS. So you might want to request that just for comparison purposes. But this is really a key benefit of SATK is that we directly compute the peak for you. You don't have to do additional post-processing to get those peak results. And I like to go into a bit of detail here because we also have this von Mises method at the bottom of the dialog. And I like to explain that with a slide. So what we call derived results, so von Mises stresses, principal stresses, composite failure metrics, these all do not follow Gaussian distributions. And to explain a bit, in a random analysis, the input is assumed to follow that Gaussian probability zero mean distribution. But these results, because of the fact that they're calculated with these equations, they do not have a zero mean and they are not Gaussian, so we need special algorithms to calculate them. And that is another key differentiator of SATK. We can calculate these results in a statistically correct way and also do it very quickly with our proprietary PDQA algorithm. And in industry, sometimes some assumptions are used. So in industry, they might take RMS results and just multiply them by 3. But that's actually not statistically correct. And we explore that in one of our conference papers referenced here. So I always like to emphasize that that is one of the big benefits of SATK is that it's both faster and also more accurate. I will also mention one other item in the dialogue, which is regarding the integration scheme. And it actually also relates to the question we got in the chat about frequencies. So most commercial codes require you to specify excitation frequencies, but SATK actually determines these automatically to ensure accuracy. And at the white paper that we'll reference at the end of the presentation, it discusses this in more detail and gives an example of some of the pitfalls that can arise on this topic. So with that, I've specified what I need in the analysis parameters section. And maybe I see one more question in the chat. I might come back to that at the end of this portion of the demo. So I'll just finish here with the last step, which is to specify some output requests. And I'll show here you can specify multiple output requests, and they can be either for contour plots. So I'm requesting accelerations here for something that can be plotted in FEMAP or SimCenter 3D. And I'm also going to request function results. So in the same run, you can request both function and contour results. And I'm going to request some PSDs for accelerations at some specific nodes of interest. And I'm going to export this to both Excel and to a format that can be post-processed in SimCenter 3D. And that frequency plotting at the bottom, like mentioned before, is just really for the resolution of the graph and doesn't affect the calculation of peak results. Some other results that we'll request are things like stresses. So the von Mises stresses will come from there. We will also request margins of safety. So we define those stress cases up front. So this will compute margins with this equation based on the allowables that we brought in at the beginning of the demo. So that's a nice output to directly get that result instead of having to manually hand calc that at the end. And we have this unique ability to compute composite failure metrics. So this would be like a first pi failure. And so I'm going to request those results on the composite portions of the model. And importantly, we have this new fatigue analysis capability. So I'm going to request fatigue damage and life results on these groups. So that's where the fatigue properties will come from. And you'll see here we have a choice of a few different fatigue methods. So to go into a bit more detail, narrowband, that's typically used in acoustic fatigue where loads tend to be narrowbanded, so just a couple of frequencies or one narrow band of frequencies. That method is too conservative though for a lot of structural analysis. It tends to be more broadband. So that's where the other two methods would come in. So Dirlich and Steinberg are meant more for broadband cases. So Dirlich is generally what's recommended, and Steinberg has been historically used more in the electronic and PCB industries and is based on sort of three-band method. And if you're interested in more background and some of the equations used for this fatigue analysis, you could check out our documentation where we go into a bit more detail. And also worth mentioning, these are based on a stress life method, as you may have seen from the material data. And finally, we specify a equivalent stress to use. So often we use von Mises and a duration. So a lot of these tests are a minute or a couple of minutes. So I'll put in a 60-second duration. And with that, I can go ahead and launch the analysis and run it. This particular model took about 30 seconds to solve on my laptop. And as that goes through, I'll just have a quick look for any questions that came in.
You could answer the question that came in. How do we decide on a cutoff frequency for normal modes analysis vis-a-vis frequency defined in the random load input?
Yeah.
Andy, would you like to answer that, or?
I think it depends a bit, because I guess ideally you would want to have your modes going kind of well above the highest excitation frequency, but on a lot of models that may not be possible. So it does depend a bit. I think also there's both the question of having enough modes and also having enough effective mass. So it's a bit of a case by case.
Right.
Question.
So typically, I think yes, you have to go above because random vibration is calculated most normally by superposition. If you truncate it too early, you'll miss dynamic amplification. And if you go too far, then obviously you're overdoing computational resource, right? So, yeah.
Exactly. All right. And yeah, I don't see any other questions yet. So just to summarize, so we've just run through the random analysis setup. We covered some of the new features, the new modeling objects. I'll talk about the new input file in a second. And just to reiterate, some of the key benefits are things like the integration scheme automatically determines the frequencies, the ability to directly compute peak results quickly and accurately. I didn't mention it, but the solver is multi-threaded. It'll use all of the threads that you have available, so that is quite nice as well. And I thought for any of you that are existing users, I would just briefly mention we have this new input file. It's still text-based. It's probably even more readable than the previous one. I wanted to mention it automatically gets saved as you work in SATK, so any inputs automatically get saved in that file. All the processors, sine, random, are using the same file. And it's a bit easier to load existing analyses. It has a reference to the OP2 file that you used. But if you like working in batch, working with these text files directly, you can still do that. So a lot of our customers, run many analyses in batch. So that's something you can still do. And if you are an existing customer using the previous format, you can still import that data to reuse it. And if you're interested, this is the TOML format is the format that's used by this file. So I will now go to the next survey question. And so we're interested in any pain points that you have regarding random or sine base vibration. We've listed a couple that we hear quite often, but we're definitely interested if there's something that we haven't listed, we'd be very interested if you could put that in that other category as well. So I'll give you a few seconds for that. Yeah, and hopefully usability is one we hear a lot, and I think that's something kind of nicely addressed by SATK, the fact it is a dedicated tool. I know some of our customers don't run random analysis for months, and then they can come back and still do it in SATK. So I think I've got a pretty good quorum of results here, so I may share it right now. And just having a quick look through the results. So actually fatigue is a concern for more than half. Same with super elements. Same with shock, actually. Especially for shock and fatigue, if you have any particular interest there, might be interesting to put a question in the chat on those. I see, notching, I see about 37%. That's something that comes up quite a bit as well. All right. Oh, great. I see you. Yeah. One is I see some of you are happy that the input format has changed. Yeah, I think it's quite a bit more intuitive now. All right. So I'll close that poll, and I'll go now into part 3, post-processing. So we've run that random analysis, and now we can post-process. I will do that in some Center 3D in this case, returning to where I started. I'm going to load in some of the contour results. So this is coming from the OP2 and a bun file created by SATK. Typically, I'll look at accelerations to start with. I actually use a lot of post templates to put these in nice units and nice scales so I can see my accelerations in units of g here. We've also got that acceleration magnitude, which is something kind of uniquely calculated by SATK. We have our von Mises stresses as well, so we can see our peak stresses directly, so no hand multiplying by 3. And we requested those margin of safety results. So this is in percentage, so we can kind of quickly identify where we might have negative margins and where we might need to add some reinforcement or make changes to our structure. So we do see some negative margins in this particular model. We also had that unique ability to compute composite failure metrics. I personally like to look at the strength ratio, which is kind of like a safety factor. So anywhere that's less than 1 would be failure, and above 1 would be safe. So we see actually in ply 1, we do have some regions which are failing, and the same in our other plies. So that's quite quick to identify, and often you can envelope those results to find the critical ply. And here's that new fatigue damage result. So basically anything above 1 would have failed within that first duty cycle. We do see we have kind of a critical element there, and there's only really a few elements in this particular model that have significant amounts of damage. And inverse of damage would be life, so you could also look at kind of number of duty cycles that your structure could survive. And in my results tree there, I have this result for the different materials. So this particular one is for the aluminum, but my results have the other materials and the other 2 load cases as well. So those are some examples of the kind of graphical post-processing we can do. A lot of our customers also like the Excel or text-based outputs. So I'll give some examples of that. We can output here to this Excel file, which has an echo of your inputs, which is nice for traceability. And then you can go in and look at, in this case, the critical margins of safety. So this is sorted by the most critical first and by material. So this is kind of really nice for any reporting requirements, and it's already in a kind of nice format. So I've got my margins for my different load cases, and I also have my new fatigue results. So we see here it highlights the most critical element at the top, and then up to the damage threshold I input, I have all of the other elements with significant damage underneath. And once again, this is sorted by stress case and by load case. So that Excel file gives you kind of a nice summary of critical results. We also have another Excel file for function data. In this case, I requested PSDs at some specific nodes. So this kind of information can be useful for workflows where you might need to do notching, or if you're requesting interface forces. And I'm showing here that we provide a macro to do some additional formatting if desired. So here it automatically created some graphs on additional sheets. So right away I've got like my PSD in G squared per hertz. So those are a few examples of some of the typical post-processing that we do. So support for contour plots in mainly these two tools. Function plots output to Excel and text files, which is useful for if you're doing additional post in your own tools. And always good to emphasize that we directly output those peak results. We didn't have to hand multiply RMS results. And we also got the margins. We didn't have to do additional post-processing there as well. So maybe what I'll do is just kind of quickly summarize what's new. So you saw a bit of that in the demo. So really the new SATK file format, the modeling objects. So this is just big kind of ease of use enhancement, easier to reuse that data. Improved importing, like you saw the importing of the SATK file from material data, or importing of the groups, or you can import SATK files or IMP files, so a lot of data reuse potential. And biggest improvement is really the addition of fatigue for random analysis. And I might take another pause as I do see more questions coming in. Yeah, actually, so Mohan's asking, yeah, it is available as a standalone solver that can run in batch mode. So that is supported. Feel free to reach out to us if you want more info on how that's done. But yes, you can do that on Windows or Linux. One other question regarding fatigue damage on different. Yeah, so currently we present fatigue damage on different materials and different output vectors. Correct. So yeah, in the demo, maybe you saw I had fatigue 1, 2, and 3 for my 3 stress cases. So that is currently how we format it. So I think that's a few of the new questions. Yeah.
There was that question on mesh refinement and the role that it plays. Yes, it does. Mesh refinement does play a very important role. I think primarily, I can say that fatigue is very highly stress sensitive, and stress is mesh sensitive. So yes, there are some guidelines. At least have 2 to 3 elements across stress concentration areas, or keep element size less than half or 1/3 where on a fillet. Use solid elements for fatigue critical areas instead of shells, unless it's very thin. Yeah, there are there are certain recommendations. Apparently I believe in the NASA recommendation also recommends 6 elements per wavelength at the highest frequency of interest. And you make sure that essentially for PSD fatigue, you make sure that it's fine enough to capture higher frequency mode shapes. Yeah, there are some guidelines. We can definitely talk in detail. Thank you.
Excellent. Thanks. So I think those are all the new questions I see for now. So for the audience, we have one last question. So we would be interested to know if you are interested in more information, yeah, how do you like to learn more about SATK? So yeah, please let us know if one of these three would be of interest to you. So I'll give you a couple seconds to respond to that. And while that pulls up there, definitely if there's any other questions that you have, feel free to start putting them in the questions.
Oh yeah, one more came up, Andy, as we talk. Does SATK handle sine fatigue? And I'll take
Oh,
that.
great.
That is on the plan. So the answer to that question is, how soon do you want it? We have it on plans for the next release, and if there are more specifics that you want with reference to sine fatigue, please don't hesitate to reach out to us.
Excellent. Thank you. So with that, speaking of questions, that really brings us to the end here of our webinar. So we'll take questions in a moment, and I'll just mention the contact info for Mukund and myself is on screen. There's this white paper I mentioned, which has some nice benchmarking of SATK against Nastran and talks about a lot of the challenges in random analysis. And we also have some exciting upcoming events. So a colleague of mine with a lot of experience in optimization and certification by analysis is giving a webinar on accelerating aerospace innovation, where he'll talk about MDO and MBSE. And in addition to that, we have an in-person event in Orlando at the beginning of October. This is geared especially to the aerospace and aero engine industries. So we'll have some customers presenting, and I will also be giving another presentation going into a bit more technical depth on SATK. So if you're interested to learn more about these events, we have a link here on screen. And yeah, now we'd be happy to take questions. And thank you for your interest so far. So keep an eye on the questions. Okay, so I got one good question here. So is design sensitivity analysis and design optimization capability interfaced with SATK? I don't know if you'd want to comment on that, Mukund.
No, not it's not interfaced with SATK at this moment, but we'd love to talk to you sometime and understand your needs. I guess we will wrap it up at this point of time. I would like to thank you all for attending the webinar. Thank you very much, Andy, for demoing the product. And for everyone else, please don't hesitate to reach us in either of these ways. Our emails are out there. And if you have any other specific questions, we'll be very, very glad to help you. Once again, thank you. And with that, we shall close this webinar.